Hey everyone, here's Simone from the studio. Welcome to this new video. This time, I want to introduce to you a creation of mine. It's the ClothPOP Pro. You may already try the free version. If you didn't, please go to my Patreon. It's there for free for you. And today I want to introduce to you the Pro version. The Pro version is something you have to pay. So there is a website. The link is in the video description, and it has a cost of €10. Once you pay and you register with your mail, you will actually get a reply from Lemon Squeezy. Lemon Squeezy is the platform. I choose where to drop all the project file and the DLL producing this operator. And once you make your order, you get a mail and a license key. The license key will be put here in the license page of the operator itself. You need an internet connection for the first time you activate it. Then it works offline because you have to ping the server of Lemon Squeezy to get approval. So again, you will get a license key. You have to copy it and put it here. You press activate and then it works. Okay. So what are the differences between the free version and the commercial one? So first of all, the free version is not commercial, so you are not supposed to use it to make money with it. And it has a cap of 5,000 points, which are already a lot. The Pro version, it costs €10. It will give you one key for 1 year, and it's actually commercial, so you can use it in actual real work. You have no point cap, so your only need is your GPU, and it has a welding feature, so you can attach stuff together. They will act as there is a joint in between them, and it's actually a bit faster, so it's a bit more optimized. Okay. What you get, since you give me €10, you get this folder. All those will be files you can download. They will be attached here in the mail you will receive. This is just a test. This is why it's $1 or €1. And you get this folder. Okay, let's analyze it. What do you have inside? What do we have inside here? Okay, we have a DLL. So this DLL is this guy. Then you have a manual. Oh, yes, we have a manual. You have to read it very, very carefully. You open it as an HTML page. And you scroll it, you read it, you can appreciate all the features and a bit of math inside of the ClothPOP Pro. What else? Yeah, there are some parameters, a lot of them, since the simulation needs to be adjusted based on what to inside. And I very much encourage you to read it. There are many features. All of them, most of them, besides the welding, are also present in the free version, and it's actually the same manual. Okay. So welcome to my shop, and this is ClothPOP. Let's analyze the folder again, going forward with the project files. Okay. Let's try internal pressure. So internal pressure is a project file that I want to show you a deformable body in no gravity with something that push it. So we will have a collision and a deformable body and a static object which is acting as a collider. That is generating a force, by the way. Okay. Okay. So this is the first example. See, we have a static object which is pushing stuff around, right? I on purpose make it not perfectly colliding because it's nicer to see, and the simulation is stable with those parameters. Let's analyze also the topology. Okay, so we are now inputting clothes, and as you can see, the cube is rotating and is like pushing the from our body around. You can throw any topology you like. Doesn't really matter. I guess triangle gives better normal, so you can see the operator is calculating the normal internally. Yeah, you see, you have a toggle for it if you don't need them. And let's also analyze the network. I try to keep things simple. So I imagine that you throw some geometry in a solver, then the solver does the rest. So I try to make it very easy for you to work with this ClothPOP simulator. For example, here I'm just doing a mass inside of it, and this is defined as static. So I'm using attribute pop to pass some attribute that you should read this before to understand how much attribute they are understood by the operator. But for now, it's very easy. I give a mask to this one, and I am telling that this cube is static. Okay, so static one, and then I define in this mask. Where it is? Okay, static. Also for. Okay. And the ClothPOP is doing the rest. What does mean the ClothPOP? The ClothPOP has some pages. Okay. The first one is define the parameter so to throw stuff from the GPU basically, and how you will smooth them out. So if I press initialize, the simulation start again, as you can see. Let's take out. Okay. So this is what you're doing. I decided to keep the substep and the solo iteration long here because you have a nicer result. And what is the difference? Okay. So it's the concept of a nested for loop. So for something, each time you pass through the first loop, you start another loop. Okay. So the solver iteration are the substep is how many times we want to repeat the process before to say it's over. Okay. And this solver iteration is how many times a substep has to work. So 2 times 2 is like 4. So we are repeating 4 times those kind of operations. The solver iteration are lighter to calculate compared to the substep for some mathematical reason. And then you can define a gravity. So now I put some gravity and make the torus, which is actually kept up from the box. And then you will see that the torus will like softly falling down because there is gravity. So I can put support. Well, and the guy is falling down. Let's repeat it. Voila. Right. Loop. If the simulation is too low for you, you have a parameter to speed it up. So if you put like 4, yeah, there is very it's rotating. Let's stop it. Yeah, I explain this later. Pop it, okay. And if you initialize it again, then will be much more. It will actually also do not take much in consideration this because it's too fast for the frame. So that make 2. Yeah, that's better. Okay. So you can have this kind of collision stuff. Okay. Page constraints. This I will speak it, I will show it in a second. This is very much important. The pin target. Um, so you can define how the constraints are built in the different way. Okay, if you use input P, then the geometry you throw in can be modified by the pinning, and if you throw rest pose, it will be calculated one in advance. It's a matter of optimization. So input P is it is allowing this to cook basically, and rest was not. I will speak about later. Okay, then you have some definition here for this deformable thingy. Okay, for example, I want this to make this curve more stiff. So if you increase the stiffness, and I say long band tall, so it tries to keep a bit the shape a bit more. And then if you're not happy on how this is keeping the shape, basically you can inflate this a bit more, or less, and then start to actually falling apart. Okay. Let's move forward because there is a lot to speak about. This is just a tiny example of how a deformable body can collide with a rigid with a static object. Very, very easy, super fast, like 5 milliseconds. Now it's doing this. Opla, you see, it's way, way more rigid. Also, when we drop it, because it's more stiff, you see, it pretends to stay and then fall down. Boing. Okay. First example done. Everybody's happy. Let's move forward. Many deformable bodies. So now you see we have a static object colliding here with a deformable body, but we can have many deformable bodies colliding on themselves. And we will now take a look. Okay, boing. We do have many deformable bodies falling down. It's nice. Yeah. Okay, let's throw this here. So we here. Ta-da. Okay. So this is an example that is showing the sound deformable body spheres and driven by the ClothPOP. So it's a cloth simulator that can also handle deformable body, as you saw before. Many of them actually. And this is like for milliseconds on like 3090. We will have really efficiently also on your CPU. Which has to be NVIDIA, so this is absolutely not a Mac plugin. I didn't have the capability to make it work on metals because I'm not a Mac owner, so this works on Mac and NVIDIA only GPU, or actually with a capable GPU, but so NVIDIA basically. But let's analyze the network, which is very simple. So as I told you, I'd like you to just imagine what you will have in reality, basically. And so imagine I am throwing some spheres. Okay, so I take a sphere and I copy a sphere in a grid. This is what we get. Okay. Since I'd like to perform a tiny bit of explosion, so I need a bit of overlap from each sphere. So I just make it a bit overlap. And you throw this into the simulator. The simulator needs to be parameterized before, of course. Let's take a look. Okay, so here I decide to have very stiff constraints, and I'd like to use the volume, so the volume can inflate or deflate by. So now they're for fluffy. If you want to put a bit more pressure inside, keep, and also the pressure is also meeting the constraints a bit harder, because if you inflate the ball, then the earth's surface tension is taking consideration the kernel. And this in the CUDA kernel, which is simulating this. Okay. See, now we have less air inside, and real time you can inflate those a little until they get the shape you like. Okay, yeah, you can see that they are not proper collided. So we do then you need to space among them. Let's speak about another parameter. Okay, good. So each point of this sphere, every one of them, has a tiny radius of search. Is searching around, and it is also getting something is colliding. Okay, by pushing the collision scale, let's put it to one. Okay, I'll do this again. You see, we're not anymore solving the actual space needed for the sphere to get separation. So they're acting as molecular, which is really nice. More, yeah, like biotic stuff. So they try to repel themselves. Okay. This is a parameter you have to tweak to your own gusto, basically, and find which is making the sphere or the object you want to draw. Um, Actually do not collide and have a very, very tiny collision behavior. So this is a parameter we have to tweak. Okay, another very, very much important parameter is object collision. So object collision is actually it's an algorithm that will be played in when you initialize. This algorithm is actually checking, hey, this point belongs to what mesh? So you don't need to define stuff. Just say, I am trying to separate them, okay, because they know they belong to all the points in this sphere belong only to this sphere, okay? So this is object collision. Let's draw the simulation without object collision enabled. It's actually parameters. They don't care much of the separating. You have to see it here in action. If I put it off, see, they stay as they are. They don't care. They overlap. Okay. And actually the structure stays stable because each object is not trying to be divided from another. They are not colliding themselves. But then while the simulation is running, you can say do it. Buying. So the simulation start. Oh, very nice. Okay. So this is how you can play around with many deformable bodies. Okay, yeah, we have a floor. The floor has a friction, so now they try to slide due to the force of the constraint, which is moving them around, and the friction of the floor is not much. If you increase it, then they will actually stay in place even more, and they need to push them hard to get the separation they need. You can play around; it's very playful. Okay. Example down. Let's go forward. Pinning. Finally, we can play around with pinning. It is super fun. My whole concept that I using when I was developing this is that basically you need to have fun. You don't need to care much. And also, even if the math is not properly 100% physical accurate, we don't care. We are not physicists. We are touch designer user. That's not something to fun. I mean, look at that. Thank you, bro. Buying. Okay. A very important thing that we can actually analyze immediately now is how you can draw attribute with a field pop. So to use it with lighting. Over. Buying. You use a field pop. Okay. Let's say you don't simulate initialize, but please show me this. Okay. So this is what is happening before the simulation. I don't know if you can see it. Let's throw some color dot, maybe we will see it better. Pin, bang. No, we don't see it. Yeah, we see it. Okay. If I go even on the side of this disaster, you have some colored points, some not. And the colored one are also rotating. Okay. You take a field pop you throw basically a tiny sphere inside of this symbol of lines, and at some point will be inside of the field, so they will get an attribute. You should name the attribute pinned. Why pinned? Because pinned is one of the attribute the solver can read. So there is a naming convention. This is why I encourage you to read somewhere. So that should be all the list of the attribute. Yeah. Okay, pinning here. Here you have pinned. Okay, so if you throw some attribute and you call it pinned, so the solver automatically knows. You can also throw them with another name, but to keep things simple, let's keep it pinned. You can throw another name like static, but static is already used somewhere else. So pinned is nice. What is allowing you pinned? Pinned is actually allowing you to move points while the simulation is running, and the solver will act based on the movement you do. So you can have things interacting while the solver is running, which is the whole meaning of this. Very important. Okay, so this box with the point. Now that we know, we also know that if I do this look, simulate play, and the guy is moving, okay, now I can use the Asimov, I can use the width attribute. So I say, hey, move only the pinned attribute. Look, here they are moving, but the simulation is not acting. Why? Because we are trying to optimize things that we should not. Basically, the rest pose is getted once when you press initialize. If you want to be able to move pointer dynamically, you should use input P. And that is, as I move it, you see this move. So then you can play around with the pinned point and move the whole constraint situation to your booster. Ooh, that's super cool. Okay. I am dropping some frame because, yeah, you know, the calculation is hard, and also because I am recording. If not with very fast, we can also trade. So it's like, it's fast. If I have the GPU cook time here, yeah, anyway, it's very fast. And also it is calculating how many, if the constraints doesn't need to be updated, it's keeping it, so kind of well optimized. And yeah, it's what that. When you start playing out, super fine. I am now on 4090, so I believe this will, I don't know, I hope for 60 on a 5070 for food. Lower GPU like a 3080, you may go around 4030, but you can lower the count here in the box pop. It's actually an issue with division bars, which is what I'm using to throw constraints. And also maybe you can deactivate like the enforcement bars. So that is like that. Okay. Can also appreciate the difference of the, let's do it again, so they still right there. And you can also appreciate some other values here. So if you want to have something more stiff, let's say, it tries to compensate the constraints. If you want to have something like very soft, you can throw it down. That is acting like this. Okay, so this is the example where I show you pinning, which is super fun. Nice. Well, and the rope example is actually to showcase the collision scale parameter. All right. So, and this spherical cage, which is really nice. Okay, so now we have a rope inside of a cage. If I press initialize, then it's yeah, it's like doing this. Um, let's copy some sphere of those points. So we pick a sphere because you will appreciate much better the collision radius in action right now. Let's copy. Yes. Nice. Okay, so we can actually see that with the size of the, yeah, let's try to do this. Okay, I will copy uh, this collision radius to this. Okay, it's not one. It's okay. We will appreciate it anyway. Okay, with this size and this collision radius, you can see that the spheres are actually touching themselves. Okay, and they pretend to have they're touching themselves because there is a constraint, but then there is some space. Let's see, I can navigate inside, and there is this kind of warning situation that want to go take space basically. And now, if I decrease of the collision, if I decrease the collision radius, you will see that the rope, each sphere composing the rope is less tough, let's say. We can call this. We can make this like less, and then you can see that the spheres are more near one to each other. This is due to the collision radius. Smaller, they get a blob, bigger they explode. There's also nice behavior if you want to make something doing this. That's great. Okay. Collision radius. You have some predefined collider, like just to throw a bit more simulation or faster. Like one bomb. Okay. So the subject is warmer that try to unconstrain itself. You can slow down the if the animation is like too much for you, you can do or this or play with the speed. So here we are damping the constraint forces, and the speed is actually acting to the simulation itself. Okay. Let's speak about the spherical case. So we have this rope trying to move, and the sphere has a radius which you can increase. So maybe yeah, we remain here at 14. So stay. We have more gravity now. And I want to show you that the spherical case being something inside of a sphere, I thought about a washing machine, a 3D washing machine. So you can spin the sphere. Look at this. So spin axis, we can make this is spinning on this axis. So the is actually doing this. Due to the friction of the sphere and the gravity, you get this animation, and then you can actually make this 0, so they will get the inertia, you pronounce it, and you can use the spinning axis to have fun with the movement. And here you have a rope made of sphere inside of a spherical cage. Okay, nice. I make the sphere so small that the rope It's not anymore inside, so it's probably not. Okay. Let's move forward. Another example. This is a stress test. A stress test meaning it's a very, very big scene. This scene, there are two gloves, two grid, two, and I am throwing some from poor body and some static object that they are throwing out a lot of time. Yeah, so the animation is so big because that I need to put it. So here we go. Ta-da. Yeah, as you can see here, we have a very intense scene where they're continuously throwing static cubes and the frogos here into these clothes. And this is also like to showcase the continuous collision detection, which is by default on, but attended. So if you throw something very, very much faster, the solver is automatically trying to compensate this, but yeah, we do have some limitation. Yeah, so I got the scene. Let's go. And this is, don't propose to run on 30. I don't know if I can run it on 16. It's 30, 40, 50. Also depends how many constraints. Usually it's I have the frame dispatching dynamically. So it takes all the memory it needs, and that is automatically allocating what needs to be calculated or not. So if objects are not moving, the constraints is not being calculated. And yeah, I don't know, I'm doing a lot of stuff here. And this, yeah, the cues are also like you see colliding with this, the format, the rope, that they actually just pin on the edges. So they act like this. Very nice. This is the stress test. This is the stress test. And okay, so now WebDD. This is only the basic, the pro feature of the operator. So all the other stuff you can read even with the free version for not commercial purposes. This one, you can't. So, as you can see here, I am welding three boxes made of constraints together, and they had a nice lip. We need to use some damping here because the joint is a 3D joint. It's fast to calculate. So you may encounter some rotation and will be some update the next month to make it look more real, but it posts like this I do like very much. And also let's appreciate the solar iteration. So, and the stiffness, of course. It is buying it. And you can bring it up. Oop. Let it pull down, buying it. Stiffness of 0, they extend to infinity. And then we try to have fun. Okay, so let's analyze the attribute here and where you can use it. Yeah, attribute. You have an attribute page, and I weld and joint. You can say off, but this is calculated by initialize. So I can make this that they go down to infinity. If I say on, then I need to initialize again. This must be done for performance reason when you press initialize. You can then move those up if you talk to me now, but it's better to not do it to break the simulation. So what is anchored to what is the define on init? You can change it in real time, which is a basic stuff for a simulation. I will improve it, but yeah, how we are hanging stuff together. How you can hang stuff together? You have to use ClothPOP to draw it. So let's say not simulate. Hit this. Okay, ta-da! So this is the structure we are defining, and I'm using also a feature which is ClothPOP PRO. So automatically everything, when you throw something, since I have an algorithm that is reading the geometry, understanding stuff, I know which is the upper part, basically. So if you push into row, what it will take the higher point you have one and keep it. Okay. This is why we are hanging stuff without having pinned, because we don't want to have pinning it for it. And those red things here, they are defining the WebDD. The WebDD must be different for each weld. All right. So let's take up the points. Dot off. Okay. And I want to show you the text, because with the text we can appreciate the numbers, WebDD. So here, hope you can read it in this mess, but it's written one. What? Let me make it bigger. Let's see. Yes, we can. Okay, so here is the definitely pretend one. If we move at 0, 0, 0, 0, 0, 0, and right here there is a 2. All right. So maybe go out over. Not there to be. No. Okay, so now you can actually read 2 where the points are. Okay, this is more visible actually. One. And everywhere else is 0. So where is 1, you define a way. That's all those points, they need to stay together. And of course, do not collide among them, but stay together. So these two things together make the simulation just so. Okay. How to define it properly? You need to use a point pop. Point pop, it has a setup case. You need the size because I'm using a box, so I can extrude it. And to range, it's very important, because with to range, you can actually define, okay, point 1 has a range to 0 to 1, so we'll output 1. Point 2 has a range of 0 to 2, so we'll output 2. And definitely, since it's a Boolean, so it's not a int, it's not a float, it's an int, it's 0 or 1. Are you pinned or not? Are you welded or not? It's good that you don't have transition range. Keep it 0. Relax. After you do this math on your geometry, you can then simulate some constraints. Okay. So, hope you like this operator. It took me some months and a kind of big amount of token with Claude, so to make, so I'm not the only one that made this operator. This operator was actually mostly white coded, but all the knowledge and the optimization I put and the love I put in this operator, it's a lot. I guess that €10 is not even is not a fair price for me. So I kindly encourage you to buy this operator, so to keep my journey on doing free stuff on my pattern possible. This year was not very much good working wise, so any support is welcome. Thank you very much for your attention, and we see each other in the next one.